Now, there are some configurations that are not what you might expect. And I want to talk about some, and the example might be chromium. So if I look up chromium on my periodic table, you can see it's here. It's an atomic number of 24. And I can see that it's going to have 4s2 and 3d4 is what I would think, isn't it? But let's write down the electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6. How many electrons am I up to now? That's 10, that's 18. I've got another 6 electrons, haven't I? And I'm choosing between the 4s and the 3d orbitals that I know are very close in energy level. Now, another thing to know about our electron configurations is that there are special stabilities. Full. So if we have a full subshell, if we have empty subshell, they are stable, but the one that you may not realize is half filled. And so if I look here at my options with chromium, I would think that if I was just following along this numerical pathway, I would think that I would have 3d4 and 4s2, wouldn't I? But in actual fact, I don't have that, because I can actually half fill both of these. If I go instead 3d5, 4s1. Okay, so instead of completely filling the 4s and then not quite half filling the 3d, it's more stable to have them all half filled because these are so close in energy level. Okay. I guess another thing to look at is the formation of ions, especially with now we're going to be thinking a lot more about our transition metals. So we didn't really think of them at all in Psi, and now as our inorganic component, we are going to be focusing a little bit more on the transition metals. Now, you might remember when we were using like our manganese and our chromium ions, we said that they had multiple oxidation states, and there's a good reason for that. If we think about manganese there, and it's next to chromium, or even if we think about chromium, now we'll do manganese. So manganese, then I can make this into manganese. By just putting one more electron in the 4s2, because now, the reason why this is good for manganese, this one is half filled, and this one is completely full. So that's obviously going to be stable configuration for manganese, the element. Now, the thing with all of our transition metals, they can all form 2+ ions, and they do that by losing their 4s electrons. our standard rule for ion formation would be last one in is the first one out. And that would make sense if we're thinking about energy levels, because the last one in is at the highest energy level. And so you'd think if you're going to lose it, that's the one that you're going to lose. But for our transition metals, even though the 4s orbital is at a little lower energy level than the 3d, again, if we lose them, then that's empty. And we have our remaining electrons in our d orbitals, or subshells, and so there is a stability to the ion there. And they all do this. So it doesn't matter which transition metal we're talking about, it's going to be the 4s electrons that they, the 2 electrons in their 4s that they're going to lose. Manganese can end up with an oxidation state of 7. Can we see why? Yeah, because we're going to lose those 2, but then we can sequentially lose all 5 of these. So that's why manganese and our transition metals have multiple oxidation states, because of that ability to lose sequential electrons from the d orbital as well as the 4s2. Now, even though we generally refer to this D block as the transition metals, these metals here aren't transition metals because they only form 2+ ion. And a transition metal has to be able to transition between multiple oxidation states. So these ones don't, because their D is full. They've got 10 D electrons, and so they're only going to lose the 4s electrons when they form an ion. Does that sort of make sense? Okay, so if let's have a think about nickel then. Nickel is 28. So if I'm writing out the electron configuration, I'm going to go through this process. It's pretty quick to get through here, and you can sing the song, 1 S2, 2 S2. I sing it all the time. And we have to add up our numbers here up to 28. So what's going to be after 3p6? Well, we would fill a 4s2, but when we're writing it out, we will try and write it out in order of principal quantum number. So that's 10, 18. So we need another 10. So it's going to be 3d5, 4s2.
Oh, would it be 8?
8. Yeah, it would be if I was actually adding it up to 10. That is in the ground state. Sometimes we're asked to represent, well, let's look at what it's going to look like as an ion. We'll just do the nickel 2+ ion. That's it. It's lost those 4s2 electrons to form the nickel 2+ ion. Both of these in the ground state. Now, an excited state, I'll pick a different element and go back to something quite as long. Let's think about magnesium. Okay, we've got 12 electrons that we've got to put somewhere. Excited state. These inner electrons are going to stay in there as close to the nucleus as they can. It's 10. There we go. That would be an excited state. Of course, we've skipped. I've put 2 up in the 4 orbital. Or I could have gone anything like that. It's indicated that the outer electrons, the ones furthest from the nucleus, are the ones that are going to be easily excited, and anything that isn't in that filling order of the lowest energy level would indicate that it's in an excited state. Sometimes you might have something that's a little bit more complicated as far as how it's organised, where the electrons are. And you might be asked to say, which element is it? Well, it's easy to find what element it is, because all we need to do is count the numbers up there and find out how many electrons there are. Is it an element or is it an ion? And so we can then work to see, well, if it's an element, that's going to be the same as its atomic number. If it's an ion, then we have to think, has it donated or gained electrons to form that ion? And we're going to anticipate normal things happening. So our ions that normally form, you know, like the O2 minus ion, or any of our metals donating electrons, that's what's going to happen. We're not going to come up with a crazy thing like this, okay, where a sodium has gained an electron. So we have to be mindful that our chemistry understanding still applies in this case, and that our metals are electron donors. Okay, so there are... Yeah.
Is there any possibility of them jumping up to like 5s or 5p?
Yeah.
So it doesn't matter
The number doesn't matter. As long as it's not in the filling order, it will indicate it's in an excited state.
Yeah.
And then you might also be asked to rewrite it in a ground state. And then you would have to put the correct number of electrons back into that ground state. Any other questions? Okay. Now, have I